Assalamu alaikum everyone. Today we want to start time domain analysis, which is chapter 4. So far we have learned how to do the mathematical modeling of a control system from the chapter 2. But in this chapter, so we will analyze the mathematical modeling in the time domain. So it means that we will analyze the transient response and steady state response. So it is like this. So let's start. Today we're studying the time domain analysis. Okay, chapter 4. So what we have learned from the chapter 2 is we had a control system, okay, and a control system CS. So what we learned in chapter 2, so from the control, so we have done the mathematical modeling, of the system. Okay, then in this chapter what we need to do, is we want to analyze the system. So why we want to analyze the system? Because we want to check the characteristics yield is according to our desired behavior, whether the characteristics yield the desired behavior, okay. So it means that the objective of the time domain analysis is the performance of the system based on the time, is to analyze the performance of the system based on the time. So the objective, what is our objective? It will be, if we know our objective, then it will be easy for us to understand that. So the objective of the time domain analysis is the objective of the time analysis is to study the performance of the system based on time. Okay. Now let's start our second part, time response analysis. Time response analysis. I think you can see. Yeah, you can see. Let me make it here. Yeah, time response analysis. Okay, so what do you understand by time response analysis? It is the actually same definition like time interval analysis. It is the same thing. So just is in more elaborately, if we elaborate more, a bit more, it means that I have written on your slide, you can check from here, the time response analysis means the behavior of a system in respect with the time when a specific input signal is applied. So what do we understand by this? We understand that we want to analyze the behavior of a system, I mean the output behavior of a system, with the increasing of time, yeah, when an specific input signal is applied. So that one actually we call it the time response analysis. So there are two types. There are two types of time response analysis. Number one, we call it transient response. Transient response. We have just said right at the beginning of the class that we need to analyze the transient response and the steady state response. Number two is steady, S-T-A-D-Y, state, S-T-A, response. Remember these two terms we can also call is a natural response. It's written on, I have written in your slide, natural response, and another we call it force response. Force response, right? Let's see what is transient response and natural state response. So if we check our slide, never mind, let me draw for you. So let's say if we have a system and the output of the system is like this. So we can say that this is our CT, this is our output response, this is our time. Of course, this is our time. So we can see that until here, with the increase of time, the response are changing. But from here until infinity, maybe infinity, with the increase of time is almost constant. So this one we call it transient response. Okay, until here we call it transient response, and from here we call it steady state response. PONSE. Yes. I hope you understand, guys. If you have any more question or anything, tomorrow we can discuss during our live class. So mathematical representation we need to check the mathematically we can write the time response mathematically. I think I should write in a bigger font. Mathematically we can write the time response time response let's say YT. Okay, time response we call it YT as time response as YT equal YTT plus YSST. It's already given in your slide. Let me show you a glimpse. So this is the one in the slide. I will give you later. I'll upload you also. Then we can call it this one, the YT. We call it, this is our output response. This one we call it transient response. And this one we call it, this part we call it steady state response. Sorry. Okay, this is our mathematical representation. Now our question is how we can evaluate the output response of a system. This output response, how we can evaluate. So the next part we can write evaluate. Is also mentioned in the slide. Yes, it's there. Evaluate the output response of a system. That means Y of t, the output response of a system. It's actually very simple. I tell you, it's a very simple word. I want to tell you is that, let's say you have a one signal. The characteristics is like this. Okay, the question is how you are going to analyze this signal. That's all. Now come back to here. Evaluate the output response of a system. Cannot see, right? Okay. Yeah, that's all. In order to evaluate the output response of a system, we have two methods. One is the differential equation, and the ILT, the inverse Laplace transform. So, but in this, but last time in chapter 2, we basically applied the inverse ILT. I mean the inverse Laplace transform. Here also we will do the same thing. We will also apply the inverse Laplace ILT. That's all. So example is so let's see an example. Example is first order system for first order system. You see first order system. Oh, so, okay, you understand, right? This one again, evaluate. I mean, how you want to evaluate the output response of a system. So as I say, there's two methods. One you call it the differential equation, solving differential equation, solving differential equation, and another one we call it ILT, okay, inverse Laplace transform. But basically I will show you the ILT because that's what we learned in our chapter 2. Now let's see the example. Let's see the example here. So example is first order system for unit step signal. First order system for unit step signal. Before I go to the example, okay, let me show the example first. It will be easy for you to understand. So we have one transfer function. This is an open loop system, you know, which we call it R of S, which is an input response, and this one is CS, output in an S domain, right? This is an S domain, and our gain is A over S plus A. Okay, so the transfer function we know very well, this one. So the transfer function, we can say T of S equal CS over RS. Can you see? Yes, you can see now. CS over RS equal A over S plus A. This one we know, right? We can easily write. This is the actually transfer function. So okay, now come back to the definition. So what is the first order system? What is the first order system? The first order system is if the maximum power of S, again, if at the transfer function the maximum power of S at the denominator is 1, then we can call it a first order system. So see further, CS over RS equal A. If I take A as a common, so it will be 1 plus S over A, right? So it means it will be 1 over 1 plus S over A. So you can see here at the denominator, you need to consider the denominator. At the denominator part, here the power of S is 0, and in this case, and here in this term, the power of S is 1. So if the maximum power of S is 1, so this function, this system, we call it the first order system. So this is the way we can know this system is first order or second order. Now let's proceed. I place it here. So we have CS over RS equal 1 over 1 plus S over A. So this one we want to write 1 over 1 plus tau S, where tau equal 1 over A. we want to write like this. Okay, go to, so you can write CS over RS. Therefore, you can write CS RS times 1 over 1 plus tau S. So we can make an equation number 1. This one equation number 1. So this one we call it, this equation basically, this one we call it the fundamental of the first order system. Okay, this is the fundamental of the first order system, or this one actually same. Now it is the, since we are determining the time response of a first order system for unit step signal. If you remember that, just we wrote the title. Where is it? Yeah, this is here. You can see or no? You see the first order. So basically we are determining the first order system for unit step signal. So unit step signal means our input signal in the time domain, that means R of t equal 1. Okay, so it means that yeah, I mean 1, or you can write u of t equal 1 when t is greater or equal 0. So that one we already know, right? The last time we have also, this one I think also we learned in our SPM that u of t equal unit for unit step u of t equal 1. So if we take the time what is called R of S domain, so it will be the Laplace transform of ut. It means that Laplace transform of 1, it means that is actually 1 over s. Is actually 1 over s. Right? For the unit step function, our input signal Rs will be 1 over s. Even you can see from the Laplace table also you can understand. You see the Laplace, you remember the table I have given to you last time? I gave it to you, which is 1, and this is actually for the unit step function, it will be 1 over s in the s domain. So that's the reason we are writing R of s equal 1. So then R of s, we are writing R of s equal 1 over s. So we can replace the value of R of s in equation number 1. So equation number 1 is here. C of s equal R of s times 1 over 1 plus tau s. So we write here again C of s equal, you can write it here, replace R of s at R of s equal 1 over s at equation 1. You can write like this. So C of s will be 1 over s times, where is it, 1 over 1 plus tau s. Okay, so we can write 1 over s 1 plus tau s. This is C of s. Very good. We have already the C of s output signal in s domain. So this one we need to convert it to the time domain, because we are doing the time domain analysis. Definitely we have to that is our main objective. We have to change it, we have to bring it to the, we have to convert it to time domain. So if you want to convert from s domain to time domain, you know this one, there are two methods, as I said, differential equation or ILT. So ILT, but we will apply ILT. Okay, apply ILT, inverse Laplace transform. But you can see that you cannot simply directly apply the ILT, you have to do the partial fraction. Okay, so first you apply the partial fraction, apply partial fraction. Okay, here apply the partial fraction here. Okay, if you apply the partial fraction, I will not show you the partial fraction because you already know how to do it. Then finally I will get C of S equal 1 over S minus tau divided by 1 plus tau S. That's what we will get. Okay, so 1 over S, yes, we can apply, we can check in the, if we check in the Laplace transform table, then 1 over S we can get 1, we know. Okay, but this side we do not have any formula like this, the tau over 1 plus tau S, but we can do like this. Sorry, if we write tau here, it will be, if you take a tau, yeah, fraction of, I mean the factorization, it will be 1 plus 1 over tau, right? 1 plus 1 over tau. Sorry, the S plus 1 over tau. So this tau cancel. You can see or not? Yeah, you can see. 1 over S minus 1 over S plus 1 over tau. This is, I think, the simple for you. Just like this. Now you can see it's a 1 plus S plus 1 over tau. This one we can apply ILT, inverse Laplace transform. If you apply the ILT now, I can show you from here. This, you see this one, 1 over S minus A. So this it matches with this formula, which is e power of AT, right? And this one you already know, 1 over S is for the 1. Okay, so that means we are using the number 2, this formula, number 2, this one. Okay, I show you very detailed so that easy for you to study. That's it. Okay, so apply, if we now we can apply the ILT. If we apply the ILT, then we will get C of t. See the output, now the output response is coming. It will be 1 minus e power of minus 1 over tau t times t. Okay, so this is our actually desired response. You can see now, if we check our this one, you see yt, actually yt is here ct, same, yt equal ytt plus ysst. So ytt is our, actually this one is our transient response, and this part is our, this is our output response, this is our transient response, and this is our, this part is our steady state response. Now let's go further. We want to do some more analysis. Let me check the slide, how it is moving. Yeah, okay. Now you see that when tau equal t equal 1 over a, because we know that tau equal 1 over a, so what happened, we want to find the value of this one, e minus 1 over tau t times t. So at this moment our t equal 1 over tau, as I said, the t equal 1, sorry, yeah, t equals what is called 1 over a. You can say t equals to 1 over a. We place it here. Okay. it will give us e power of minus 1. Actually same thing, t power, if you give this t equals to 1 over tau also same, because this is a. That one will give us 0.37. Okay, the value is 0.37. Now C of t will give, so C of t when the value t equals to, so that means C of t equal will be 1 minus this one, right? E power of minus 1 over tau times t, which is 1 minus 0.37. Oh, you can't see, sorry. This is a 0.63, I think. Yeah, 0.63. So that means C3 I'm getting 0.63 when t equal 1 over a or 1 over tau. It means that, so what do you understand why we did this one? So this one we call it this a, or this one we call it the time constants of the response. So this is called the time response, sorry, the time constant. Can you see? Yes, you can see. Time constants of the system, no, of the response. Response. So this time constant, because you can see I got 0.63, so this time constant is that, what is this? So it is the time. So what is this time constant? So this time constant is 0.63. So what is this? So it is the time that takes for the step response. I'm still writing even though it's written in your slide. Response to rise 63% of its final value. So we see the graph. This is our graph. This is our graph. In this graph, you can see that this 63% of the time of the final value at t equals to 1 time constant. 1 time constant means this one, 1 over a. That means 1 time constant. This is the 2 time constant. This is the 3 time constant. This is the 4 time constant. The 5th time constant, like this. So 1 time constant is actually taking 63% of its final value. That one we got it from the analysis. We have further, we call it the rise time. We have rise time that we need to analyze. Rise time, guys, you need to check your slide, because if you only see my video, then it may be will be difficult to understand. So you need to check the slide also, because slide I already mentioned all of these things in a detail. So what is the rise time? What is the theory of the rise time? Rise time we call it T of R. The rise time is defined as the time for the waveform to go from 0.1 to 0.9 of its final value. This is actually the theory. So we need to remember that this is 0.1 to 0.9 of its final value. 0.1 up to 0.9. This is actually our rising time. You can see from the graph also. You see from the graph 0.1 to 0.9. So if you take this part, so this part will be your rising time. So how long the rising time is? 2 time constant, or maybe more than 2 time constant. I don't know, you can see or not. Just let me make it bigger. Yes, you see that it is 0.1 to 0.9. So the graph you see from here, this is taking for the step function, for the unit step function, it is taking almost 2 or maybe a little bit more than 2 time constant. How? So let's analyze. It's already mentioned in your graph. It is, sorry, in your slide. How it is coming? It is how we. So let's calculate the rise time. I have some space here. So we say that the waveform to go from 0.1 to 0.9 of its final value, of course, of its final value. It means that C of t you have to consider 0.1 and C of t you have to consider 0.9. And for the rise time you have to find the difference, because in between is the rising. So if we find, let's say for C of t, if you place C of t equal 0.1 equal the equation, you will write it here. Equation is 1 minus e power of minus 1 over tau t. If you find like this, then you will get, let's say this is t1. So you will find here, I calculated, I think 2.3 over a, 2.3 over a. Okay, don't be confused with the a and tau. It doesn't matter actually, because a and tau is the same. It's reciprocal. It doesn't matter. And another t2, same. T2 means if you, it's just t1, if you t2, if you get it here, so this is 0.9, 1 minus e a t2 like this, then you can get t2, it will be 0.11 over a. Okay, it's coming minus or what? No. So no. So now you find the difference. So you find the difference will be, can you see? Yeah, difference will be 2.3 by a minus 0.11 by a, which is giving a, and we are getting 2.2 if I'm not mistaken, which is, that means 2.2 tau. It's the same thing actually, 2.2 a or 2.2 tau. So now you go back to the graph again, you see it is the same thing. It's coming 63, what is called is, yeah, 63%, not 63%. It is the difference between the 0.1 and 0.9, this one. Okay, you see, you can see it is 2 over a, a little bit more than that, because it's 2.2 tau. This one done. What else? Now the settling time. Settling time, we call it, is another term we need to analyze. We call it settling. The settling time, we call it TS. That we need to find. Settling time is defined as the time for response to reach and stay within the 2% of its final value. So it means that 2% of its final value, so it means that CT will be 0.98. That means 98%. The rise time we said 0.1 to 0.9, that means the 10% to 90%. But here we have CT equals 0.98, okay, for the settling time. You will do the same thing. CT equals 0.98. Then you just after the same thing you find the TS. The T will be coming, and we have 4 over I think 4 over A you will get it. That means 4 tau. That means 4 time constant. That is for the settling time. So now we go back to the graph again. You can see this is the settling time, the 4 tau. This is the 4 tau, okay, until here. So now you can see here from here to here, this is from here to here, I mean 2.2 tau, which we call it the rise time, and there's the TR, and from here to here, that one we call it TS, we call it settling time. So guys, again, before I finish, we can discuss what we learned today. So we have started time domain analysis, okay, time domain analysis. So in order to analyze a system in the time domain analysis, we need to analyze the two terms which we call it transient response, and the transient response and the steady state response. So we have known that what are the transient response and the steady state response. We have already known the definition, but you can actually get more details from the internet, because I just checked. There's a lot of the materials, the online materials. There's a lot of online materials. And also in the YouTube, I just also checked a lot of videos there regarding this. You can also watch all those videos. Then at the same time, we have we also have seen the mathematical. We have also seen the mathematical derivation of the time response. Okay, this is the derivation. We know outbound response, transient response, and steady response. Then we have said that we want to apply ILT for solving or evaluate the output response of a system. Then we have shown you the example of the first order system for the unit step signal. Okay, this is the example. This is one of the examples we have given in one system in the AS domain. So that we calculate the transfer function. So once we have the transfer function, okay, once we have the transfer function, then we applied ILT in order to get the time response of the system. Okay, finally we got the time response of the system. Where is it? So we applied partial function over here. Yeah, this one, the time response of the system. Okay, then this system, we say that this part is the transient response, this part is the steady state response, and this is our output response. In order to analyze further, because we need to analyze the rise time and also settling time. Okay, rise time, settling time. What we did, we analyzed that this way. That for the rise time, we know that for the time constant that we have found 0. For the time we calculate the time constant. Okay, in order to find the time constant, you need to place t equal 1 over t equals to 1 over a. If you find, yes, can, then we will get e power of -1, or you can also place t equals to tau also can. Doesn't matter. This doesn't matter because it's actually, as I said, it's reciprocal of each other. So e power of -1, you will get 0.37. Okay, so 0.37 is 0.37. So finally we are getting ct, which is 0.63. It means that we say that this one actually time constant, and we call it, and we call it, this is the time that takes the for step response to write 63% of its final value. 63% of its final value. Okay. Then in order to find the rise time, so we say that these values is between 0.1 to 0.9 of its final value. Okay, that means ct equals 0.1 and ct equals 0.9. Then what is my rest? Then we found the value here. Ct, we have found the value of t. Then after that we found the difference, RENCE, difference. Okay, we found the value of difference. So 2.3 divided by a minus 0.1 by a, so we are getting 2.2 a. That means 2.2 tau. So that means we call it, this is 2.2 tau. Then settling time also. Settling time, so we also know that for the settling time, it is actually ct will be 0.98. So t equal, you are getting, our time you are getting for time constant. And then after that we have seen this reflection, all this kind of reflection we have seen in our graph. Okay, as I said, you can see here that this is actually tr, this is the rise time, this is the rise time. At the same time, this is the ts, this is the settling time. So this is the way we have found the time constant, then rising time, rise time, and settling time for the unit step function of the first order system. Okay, thank you so much.